Apparently, I didn't. I'm going to do a quick sound check, uh, get thumbnail on YouTube, stuff like that, in the proper playlist. See what's going on here. Waiting to hear something. Okay, so today is weird science. Oh, that echo or that background audio is picking up big time on YouTube. And YouTube. There we go. I got the thumbnail. Now I can mute out YouTube. Gets distracting. I'm supposed to be doing an audio test. When I hear my voice, it's hard for me to concentrate. So let me hear what's going on D Live now. Sounds good on D Live as well. All right, gonna run over to Twitch, see how that sounds, and then Kick as well. Sounds good on Twitch. Check and see if Kick is up and running. I usually check D Live first because that's the one I usually have problems with when it comes to streaming. Today is kind of interesting because I've got a whole bunch of uploads going on right now with Rumble. Sounds good on Kick as well. So we're up and ready to go there. I've still got to get my readings set up for my topics, I should say. Set up for weird science, and I should be ready to go. All right. So here we go. I just gotta wait for him to kick in. Everything, like I said, is running a little bit slow on my computer right now because I'm in the process of getting a lot of stuff uploaded. I had to do a rush on it. I'm pretty much at the end of my memory, so it's a matter of doing a quick job on there. So say it whenever I get all this taken care of. I'm finally getting down to where I need to be. Okay, I've got it. So we are set up and ready to go. And this is what I am going to do. I hate that on Kick, dude. I mean, like right there, the moment I freaking start my stream, all of a sudden I get some jackass that wants to send me spam saying I need to freaking pay for viewers and shit. It irritates the hell out of me. And it's like the moment I start. All right, so let me see what's happening on Rumble. It's probably important that I check that out. Yeah, that sounds good. So we have Rumble up and going as well. So we're good to go. I'm going to go ahead and get my introduction and everything started, and then we'll get to the topics. And take 2 sips of coffee that time. Hello, everybody, and welcome to another episode of Weird Science. I'm Roger Hanson, and I am your host. Today, we are doing 3 more topics. Now, before I was going back into some historical science, some things, the history of science, basically, and covering some things. Now, I'm going to come back to more modern science and kind of go through some stuff there, and I'll have more available here in a little bit. There's a couple of things that I actually almost missed out on from earlier this year that me, Mark Edworthy, and Mr. Robot were discussing on Minds Roundtable, that I want to pull up and get on here as well, because it was a pretty interesting conversation. I believe it was in the 5th episode, maybe the 6th. It could have been the 6th episode this year, so I'm going to go back and check it out and pull up the information and get it all ready and going for one of the episodes. So with that being said, I've got all my information set up and ready to go. Things might be a little slow because at the moment I have things uploading on Rumble. I'm going to be doubling up on my WoW Talk for Rumble. For the 15-minute videos, those are going to be published, or they're scheduled to be published every Friday at 5 p.m. I've been doing it at 5 a.m. whenever the ones that I do have scheduled, but I'm also going to be doing WoW Talk every Friday at 5 p.m., 15-minute videos. So if you guys want to check those out, you can. I've been going through and trying to organize the playlists a little bit better. I found some of the videos on channels that I have on there that they weren't supposed to be, so I went through and changed them around. I haven't done it to all of them. I'm still working on it, Mark. Just so you know, Mark Edworthy is the one that brought it up to me. He keeps bugging me about it every time I get it. He gets a chance to, too. Every time he remembers. So I did do some work on it today, and hopefully we can get it up and going and ready, and everybody will be happy. So with that said, let me go ahead and take another drink of my coffee, and I will start with the topics. The Higgs boson, often called the God particle, represents one of the greatest triumphs of modern science. It is not simply another addition to the zoo of subatomic particles, but rather the capstone that confirmed how mass itself arises in the universe. Without it, our theoretical picture of reality would remain incomplete, leaving us unable to explain why stars burn, why atoms exist, and why matter possesses substances. Its discovery required decades of speculation, international cooperation, and the construction of the most complex machine humanity has ever built. In telling its story, one must journey from the abstract realms of quantum theory to the heart of a colossal underground collider, while pausing to reflect on the profound philosophical and cosmological implications it brings. The story begins in the 1950s and 60s, when physicists were constructing what is now called the Standard Model of particle physics. This framework sought to unify the known forces of nature, apart from gravity, under a common theoretical roof. It described the electromagnetic force which governed light and chemistry, along with the weak and strong nuclear forces which operate inside the atom. The standard model also cataloged a growing menagerie of particles, from electrons to neutrons, from protons to neutrons, to the more exotic quarks and gluons. Yet despite its elegance, the model contained a glaring flaw. Some of the force-carrying particles were predicted to be massless, and if that were true, the world would not look like the one we observe. The weak nuclear force in particular presented a puzzle. It carries the the W and the Z bosons. No, its carriers, the W and the Z bosons, were experimentally observed to be heavy, far heavier than an electron. Without a theoretical mechanism to explain their mass, the entire structure of the standard modern model threatened to collapse. The equations suggested a universe of particles flying weightlessly, never clustering into atoms or structures, a void where stars and planets could never form. Something was missing, and that missing piece haunted theorists through the early 1960s. It was during this period that several physicists proposed a radical idea. Among them was Peter Higgs, a reserved Scottish scientist who, working largely in isolation, suggested the existence of a field that permeated the universe. This invisible field, he argued, could endow particles with mass depending on how strongly they interacted with it. It was not an ordinary field like magnetism or electricity, which we can manipulate with wires and coils, but a universal sea that existed everywhere, even in the vacuum of space. The more a particle interacted with this field, the heavier it would become. Those that did not interact would remain massless, like the photon of light. In order for the field to make physical sense, however, there had to exist a particular association with it, a ripple, a vibration in the field, just as photons are ripples in the electromagnetic field. The particle became known as Higgs boson. For many physicists, this proposal solved a long-standing mystery, allowing the Standard Model to remain viable. Still, it remained purely theoretical. Higgs himself admitted he never expected the boson to be discovered in his lifetime, since the energies needed to produce it were beyond what existing accelerators could achieve. For decades, the Higgs boson remained a ghost. Experiments in Europe and the United States searched for signs of it, but none were found. This difficulty earned it the nickname "the goddamn particle," among frustrated researchers. When Nobel laureate Leon Lederman wrote a popular science book in the early 1990s, his publisher urged him to shorten the name to the God particle to make it catchier. Physicists often bristle at the nickname because it suggests supernatural association, but it in undeniably captured the imagination of the public. Newspapers and televisions began speaking of the God particle as though it were some mystical key to the universe, when in reality it was a subtle cornerstone of quantum physics. The search demanded technology far beyond what had come before. That technology materialized in the form of the Large Hadron Collider, built at CERN on the border between Switzerland and France. The collider is an underground ring more than 17 miles around, lined with superconducting magnets cooled to temperatures colder than outer space. Within this tunnel, beams of protons are accelerated to nearly the speed of light before colliding head-on. Each collision unleashes an energy burst reminiscent of the conditions that prevailed a fraction of a second after the Big Bang. Out of this violent debris, exotic particles can momentarily appear before decaying almost instantly. Two enormous detectors, known as ATLAS and CMS, were built to study these collisions. Each is essentially a vast, multi-layered camera capable of recording the tracks of energy of countless particle fragments. The detectors generate more data every second than the internet traffic of entire countries, requiring unprecedented computing power and distributed analysis. Thousands of scientists and engineers from across the globe work together to make the experiments possible. On July 4th of the year 2012, their efforts bore fruit. At CERN, physicists gathered to announce that they had observed a new particle consistent with the Higgs boson. The evidence came in the form of a statistical bump in the data, a subtle excess of events corresponding to a predicted decay pattern of the Higgs. Well, this was not a photograph in the conventional sense. It was a smoking gun in the language of physics. For Peter Higgs, who sat in the audience, it was an emotional moment. After nearly half a century, the particle that bore his name was real. Tears welled up in his eyes as the auditorium erupted in applause. The applications of the discovery are immense. With the Higgs boson confirmed, the Standard Modern gained a crucial pillar of support. The mechanisms by which particles acquire mass was no longer an elegant speculation, but an experimentally verified reality. Without the Higgs field, there would be no atoms, no chemistry, no stars or galaxies. The world would be unrecognizable, perhaps even non-existent in any meaningful sense. To that extent, calling it the God particle is not entirely misplaced. for it underpins the very possibility of matter as we know it. Yet the Higgs discovery also raised as many questions as it answered. One puzzle concerns the mass of the Higgs itself. The particle turned out to be heavier than some expected, but lighter than others predicted. This awkward middle value has troubling implications for the stability of the universe. Some theorists argue that it places our cosmos in a precarious state, a metastable configuration that could one day collapse into a lower energy state. Though such an event would occur on timescales vastly exceeding the age of the universe, the possibility underscores how delicately balanced reality may be. Furthermore, the Higgs boson does not solve the mysteries of dark matter and dark energy. Observations of galaxies and the expansion of the cosmos indicate that ordinary matter, the kind described by the Standard Model, makes up only a small fraction of the universe. The rest consists of unknown components, invisible yet detectable through their gravitational effects. The Higgs boson does not account for these. At best, its discovery sharpens the question: if the standard model is now confirmed, what lies beyond it? Some physicists some physicists hope that the Higgs could serve as a gateway to new physics. For example, if the Higgs decays into unexpected particles, it might hint at connections to dark matter. Others look at subtle deviations in its properties that could suggest supersymmetry, an extension of the Standard Model, predicting entire families of new particles. So far, experiments have not revealed such deviations, but the search continues with ever-growing precision. Cosmology, too, may be touched by the Higgs. In the earliest microseconds after the Big Bang, the Higgs field likely played a decisive role in shaping cosmic evolution. As the universe cooled, the field settled into its current value, triggering a phase transition that gave particles mass. Some models suggest that fluctuation of the Higgs field could even have influenced inflation, the rapid expansion that occurred in the universe's infancy. Others raise the speculative possibilities that different regions of the cosmos might have settled into different Higgs states, leading to multiple universes with varying laws of physics. On a cultural level, the Higgs boson highlights humanity's capacity for collective endeavor. No single nation or institution could have accomplished the feat alone. Thousands of individuals across continents contributed their expertise, from designing magnets to writing software to interpreting data. The Large Hadron Collider represents one of the most ambitious collaborations in history, akin to the moon landing or the construction of the great cathedrals, but on a global scale. The Higgs Discovery is therefore not only a triumph of physical, but also a testament to what human beings can achieve together. Philosophically, the Higgs boson challenges our sense of reality. To say that mass arises from an invisible field permeating the vacuum is to undermine centuries of intuition. We tend to think of matter as inherently solid, but in truth, its solidity is bestowed by an unseen quantum sea. The discovery forces us to confront how alien the fundamental structure of reality is compared to our everyday experience. It also blurs the boundary between something and nothing, since since even the emptiest void is teeming with fields that sculpt the properties of matter. The God particle, then, is not divine but humble. It reveals that existence depends on delicate quantum processes invisible of our senses. It reminds us that the universe could easily have been otherwise, and that our own presence as conscious beings depends on a fragile balance struck in the subatomic realm billions of years ago. Even now, researchers into the Higgs continues. Scientists at CERN are upgrading the collider to higher energies and greater luminosities, hoping to produce a more Higgs boson and measure their properties with unprecedented accuracy. Each new run of the collider brings the possibilities of surprises, perhaps slight anomalies that point to new particles, or rare decay modes that open windows into uncharted territory. The Higgs boson is both a triumph completed and a door to mysteries ahead. The Higgs boson represents a landmark in human knowledge. It solves a puzzle that haunted physicists for half a century, confirms a model that describes the known universe, and challenges us with new questions that stretch into cosmology and beyond. It symbolizes both the power of theory and the necessity of experiment, the boldness of human imagination and the determination of human effort. It teaches us that the universe is at once stranger and more wondrous than we imagined, and that even the most fundamental qualities of matter are not given but bestowed by hidden fields. The God particle is not the end of physics nor the ultimate key to the cosmos, but it is a milestone that will stand as long as humanity seeks to understand the nature of reality. Magnetism is one of the most fascinating and mysterious forces of nature. For centuries, humans have been captivated by the invisible power of magnets. From the earliest discovery of naturally magnetized stones to the modern marvels of electromagnets, hard drives, and medical imaging devices, At the heart of magnetism lies the interactions between electric charges in motion and the resulting fields they create. Understanding magnetism requires looking deeply into the concept of net magnetic charges. The patterns of magnetic field lines and the alignment of microscopic magnetic moments within materials. Together, these ideas explain why some materials are strongly magnetic while others are weakly magnetic, and why a few show no magnetism at all. To begin, let us consider the idea of net magnetic charges. Unlike electric charges, which exist in positive and negative isolated entities, magnetic charges in the form of single north or south poles have never been observed in nature. Magnets always possess two poles, one north and one south, no matter how many times one divides the material. If a bar magnet is cut in half, each half still contains both a north and a south pole. Repeating this process endlessly never results in an absolute pole. This suggests that net magnetic charges do not exist in the way that electric charges do. In theoretic physics, these hypothetical isolated poles are sometimes called magnetic monopoles, and although they have been predicted in some grand unified theories, none have ever been found experimentally. The absence of net magnetic charges has important consequences for how magnetic fields behave. Whereas electric field lines originate at positive charges, the terminal and terminate at negative charges, magnetic field lines always form closed loops. They merge from the north pole of a magnet, curve through the surrounding space, and re-enter at the south pole, continuing through the magnet's interior back to the North Pole. This continuous circulation reflects the fact that the magnetic poles cannot be separated. The geometry of these lines is not just a mathematical abstraction, but a physical reality that can be visualized with iron fillings sprinkled around a bar magnet. The fillings align themselves along the invisible field lines, creating a beautiful map of the magnetic influence. The strength and direction of a magnetic field at any point in space is represented by the density and orientation of these fields. Where the lines are closer together, the field is stronger. Where they spread out, the field is weaker. The arrows indicating their direction reveal how a small test north pole would move if placed in the field. These lines are a way for us to picture the invisible, though in truth the field exists everywhere and is continuous. They are also crucial in practical applications for understanding the behavior of magnetic fields. No, let me do that. They are also crucial in practical applications For understanding the behavior of magnetic fields is essential in the design of electric motors, transformers, generators, and countless devices that rely on electromagnetic principles. At the microscopic level, magnetism arises from the alignment of magnetic moments. A magnetic moment is a measurement of the strength and orientation of a tiny magnetic source, and it has two principal origins within atoms: the orbital motion of electrons around the nucleus and the intrinsic spin of the electrons themselves. While the orbital motion can be thought of as a circulating current loop that produces a magnetic field, the spin is purely quantum property with no exact classical counterpart. Both contribute to the overall magnetic behavior of atoms. In most atoms, the magnetic moment of individual electrons tend to pair up in opposite directions, canceling one another. This is why many materials are not magnetic at all. However, in certain elements, such as iron, cobalt, and nickel, unpaired electrons remain, and their magnetic moments can interact strongly. The alignment of these microscopic moments across vast numbers of atoms produces the microscopic magnetism we encounter in everyday life. Materials can be broadly categorized by how their magnetic moments align and interact. One category is diag- dia- diamagnetism. One category is diamagnetism, in which materials develop a weak repulsion in the presence of an external magnetic field. This effect arises because the field induces tiny currents in the electron clouds of atoms, which creates opposing fields. All materials exhibit diamagnetism to some extent, but it is usually overshadowed by stronger effects. Another category is paramagnetism, where unpaired electrons cause atoms to behave like tiny magnets that align weakly with an external field. This alignment is temporary and disappears when the field is removed, because thermal motion at the atomic scale disrupts the order. The most dramatic category is ferromagnetism, found in materials like iron. Here, the magnetic moments of many atoms spontaneously align in the same direction, even without an external field, due to quantum mechanical interactions known as exchange forces. This produces strong, permanent magnets. Within a ferromagnetic material, atoms are grouped into regions called domains, in which the moments are aligned. In an unmagnetized piece of iron, these domains point in random directions, canceling one another. But when the material is magnetized, the domains shift so that more of them align in the same direction, creating a net magnetic field. This explains why striking a piece of iron with a hammer or exposing it to an existing magnet can turn it into a magnet itself. There are other fascinating categories as well. Antiferromagnetism occurs when neighboring atoms align their magnetic moments in opposite directions, canceling out one on canceling out on a larger scale. Ferromagnetism is similar but with equal moments, producing a net effect. These variations illustrate the richness of magnetic phenomena and how they deepen on the quantum mechanical dance of electrons within solids. The alignment of microscopic moments also explains the hysteresis observed in magnetic materials. When a ferromagnetic material is exposed to a magnetic field, its magnetization increases, its domains reorient. But when the external field is removed, the material retains some magnetism. The process of reversing this alignment requires applying a field in the opposite direction, and the response of the material traces out a loop known as hysteresis as the hysteresis curve. This property is central in designing magnetic storage, transformers, and memory devices. The study of magnetic field lines in microscopic moments has also led to practical applications in imaging and sensing. Magnetic resonance imaging, for example, relies on the behavior of nuclear magnetic moments in strong external fields. The alignment and relaxation of these moments provide detailed information about the tissues of the human body, revolutionizing medicine. Magnetometers, which measure minute variations in magnetic fields, are used in navigation, archaeology, and even in the search for submarines. The Earth itself is a vast magnet with a field that shields us from harmful solar radiation and guides compasses. Its field is generated by the motion of molten iron and nickel in the outer core, a gigantic dynamo powered by the planet's internal heat. The field lines extend outward into space, forming the magnetosphere that deflects charged particles from the sun. Yet the Earth's field is not static. It shifts, weakens, and even reverses over geological timescales. These changes reflect the turbulent motion deep within the planet and reminds us that magnetism operates on both the smallest and the largest scales. On the frontier of research, scientists explore how controlling magnetic moments at the atomic scale can enable new technologies. Spintronics, for instance, seeks to harness the electron's spin rather than its charge to process and store information. This could lead to faster, more efficient computers and devices that consume less power. Other Research investigates exotic states of matter where magnetic moments behave in unusual ways, such as quantum spin liquids in which the alignment never settles into order. These studies expand our understanding of magnetism and open the door to future breakthroughs. Philosophically, magnetism challenges our intuition because it is invisible yet profoundly real. We cannot see magnetic field lines, yet they shape the behavior of matter, direct compasses, and structure the cosmos. We cannot isolate a net magnetic charge, yet the interplay of countless microscopic moments gives rise to the powerful magnets we hold in our hands. This duality between the seen and unseen, between the microscopic and the microscopic, and the macroscopic, is a recurring theme in science. In reflecting on magnetism, one appreciates how deep it is woven into the fabric of the universe. From the guiding needle of the compass to the whisper of electrons aligning in iron, magnetism shapes our world in ways both subtle and dramatic. Its study connects the quantum realm of atomic spins with the planetary dynamo and the stellar furnace of the cosmos. Though net magnetism charges may not exist, the concept of magnetic field lines and microscopic alignment reveal a universe alive with hidden order. Magnetism is a phenomena that bridges the gap between the smallest building blocks of matter and the vast structures of planets and stars. The absence of net magnetic charges ensures that magnetic fields form graceful loops, while the alignment of the microscopic magnetic moments explains the variety of magnetic behaviors we observe in materials. Together, these principles illuminate not only the nature of magnets, but also the deeper workings of the universe. The story of magnetism is still being written as new technologies and discoveries continue to reveal layers of complexity. What began as a curiosity in ancient lotus stones has grown into a cornerstone of modern science, touching everything from energy to medicine to computing. Magnetism reminds us that the universe is filled with forces unseen but ever present, guiding the dance of matter and shaping the destiny of worlds. Charge quantization is one of the most fundamental and fascinating aspects of the natural world. At its core, the idea is that electric charge, which is the source of all electrical and magnetic phenomena, does not exist in arbitrary amounts, but instead comes in discrete, invisible units. This discovery has profound implications because it tells us that nature is granular at a very deep level. Just as matter is composed of atoms, and atoms themselves are built from smaller particles, electric charge is not continuous but quantized. This principle explains why every electron in the universe has the exact same amount of charge, why the structure of atoms is stable, and why the laws of electromagnetism are universal. To understand charge quantization, it helps to first consider what electric charge is. Electric charge is a property of matter that causes it to experience a force in the presence of electric and magnetic fields. There are two types of charge, which we call positive and negative. Opposite charges attract one another, while like charges repel. The interplay of these simple rules underlies the behavior of electricity and magnetism. For centuries, natural philosophers and scientists noticed the effects of charge in phenomena like lightning, static electricity, and the attraction of rubbed amber to bits of straw. Yet, it was not until the development of modern physics that the true nature of charge became clear. The discovery that charge is quantized is most directly tied to the electron. At the end of the 19th century, experiments by J. J. Thomson revealed that cathode rays consisted of tiny particles with a specific charge to mass ratio. Later, Robert Millikan performed his famous oil drop experiment, in which he measured the charge of individual droplets suspended in an electric field. What he found was astonishing. Every droplet carried a charge that was always some whole number multiple of a smallest value. This smallest value corresponded to the charge of the single electron. The result demonstrated beyond doubt that electric charge existed only in discrete packets, never in arbitrary amounts. Charge quantization means that any charged object in the universe carries a charge equal to an integer multiple of its fundamental unit. For example, an atom with one extra electron carries a charge of -1 times the element unit, while an atom missing an electron carries a charge of +1 times the unit. Larger charges are simply multiples of this same indivisible quantity. In other words, you can have one electron, or two electrons, or three, but never half an electron's worth of charge. This invisibility is as absolute as the indivisibility, or this indivisibility is as absolute as the indivisibility of whole numbers in arithmetic. The universality of the elementary charge is a striking feature of nature. Every electron has precisely the same charge, no matter where it is found in the universe. Likewise, every proton has exactly the same amount of positive charge, which balances the electron's negative charges or charge. This perfect equality, this perfect equality ensures the stability of matter. If electrons or protons carried slightly different charges, atoms could not hold together. The chemistry as we know it would be impossible. The fact that charges come in fixed identical amounts across the cosmos is one of the strongest indicators that quantization is a deep law of physics rather than an accident. The quantization of charge also plays a central role in atomic structure. Atoms are composed of a nucleus containing protons and neutrons surrounded by electrons. The positive charge of the protons attract the negative charge of the electrons, holding them in orbit. Because the charges are quantized, only whole numbers of protons and electrons exist, which makes atoms electrically neutral or charged in predictable discrete steps. The discreteness underpins the periodic table of elements, chemical bonding, and the entire edifice of modern chemistry. Without charge quantization, the world would be a continuous soup of charge with no stable structure. The question then arises: why is charge quantized? Several explanations have been proposed in physics. One of the most elegant ideas comes from the possibility of magnetic monopoles. Although no isolated north or south magnetic pole has ever been observed, theoretical work by Paul Dirac showed that if such a monopole existed anywhere in the universe, it would automatically require electric charge to be quantized. The mathematics of electromagnetism demands that the product of electric and magnetic charge be an integer multiple of a fundamental constant. Even a single magnetic monopole would therefore force all electric charges to be quantized, whether or not monopoles exist. This argument shows that quantization is deeply woven into the fabric of field theory. Another way to understand charge quantization comes from quantum mechanics and quantum field theory. In these frameworks, particles are excitations of underlying fields. The electron, for example, is an excitation of the electron field, and its charge arises from the way this field interacts with the electromagnetic field. The quantization of charge then follows naturally from the mathematic symmetry of these theories. Gauge symmetry, which is the principle that the laws of physics do not change under certain transformations, requires charge to come in fixed units. In this way, quantization is not an arbitrary rule, but a consequence of deep symmetries of the universe. Charge quantization is not only theoretical, but has practical consequences. For instance, if solid-state in solid state physics, phenomena like the quantum Hall effect reveal that quantized nature of charge in striking experimental form. In this effect, when electrons are confined to two dimensions and subjected to low temperatures and strong magnetic fields, their conductance takes on values that are integer multiples of a fundamental constant. The precision of these measurements, accurate to more than one part in a billion, is a triumph of physics and a direct confirmation that charge is quantized. Such experiments are so precise that they are used to define standards for electric units. Furthermore, the quantization of charge connects intimately with the conversion of charge. In all experiments ever performed, electric charge is conserved. It can neither be created nor destroyed, only transferred. When a particle with negative charge and one with positive charge meet, they can annihilate into energy. But total charge before and after the process always adds to zero. The fact that charge is both conserved and quantized makes it one of the most fundamental qualities in nature, alongside energy and momentum. There are still mysteries, however. While electrons and protons carry the same magnetic or magnitude in charge, quarks, which are the constituents of protons and neutrons, carry charges that are fractions of the elementary unit. For example, some quarks carry charges equal to one-third or two-thirds of the electron's charge. At first glance, this seems to violate the rule of quantization, but in reality, quarks are never observed in isolation. They always bind together in groups that produce whole number charges. A proton composed of three quarks ends up with exactly one positive unit of charge, and a neutron with three quarks has zero charge. Thus, quantization still holds at the observable level. The fractional charges of quarks are hidden within larger, indivisible combinations, reminding us that the structure of matter is more intricate than it first appears. From a philosophical perspective, charge quantization raises profound questions about the discreteness of reality. Why does the universe allow only certain fixed amounts of charges and not others? Is quantization a result of deeper laws we have yet to discover, or is it a fundamental given of existence? The fact that electrons separated by billions of light years carry exactly the same charge suggests a unity to the cosmos that transcends space and time. Charge quantization is not just a feature of physics, but a reflection of the underlying order of the universe. Technological applications of charge quantization are everywhere, even if they are not always visible. The stability of electronic circuits, the reliability of chemical reactions, and the predictability of materials all rest on the fact that charges come in exact units. In modern quantum technologies, researchers exploit this discreteness to build devices such as single electron transistors, which control the flow of charge one electron at a time. These devices hold promise for quantum computing and ultra-sensitive detectors, pointing to a future where quantization is not just a principle but a tool for engineering. Looking beyond technology, charge quantization may also connect with cosmology. In the early universe, when matter and energy were first forming, the balance of positive and negative charges determined the large scale structure of the cosmos. The fact that the universe appears electrically neutral overall is itself a puzzle, since small imbalances in charge could have drastically altered cosmic evolution. Some theories suggest that the quantization of charge ensured this balance from the very beginning, stabilizing the formation of galaxies, stars, and planets. Even though we know charge is quantized, many open questions remain. Why do all known particles carry charges that are multiples of a single unit? Why is the electron's charge what it is and not larger or smaller? Could there exist particles with charges of different magnitudes that we have not yet discovered? These mysteries drive modern research in particle physics, where experiments at high energies probe the fundamental laws of nature. The hope is that by exploring these extremes, we may one day understand why charge quantization exists and whether it is linked to deeper principles such as grand unification or string theory. Charge quantization is one of the most fundamental truths of the universe. It tells us that electric charge exists in indivisible packets, always in whole number multiples on a basic unit. This principle was established through experiment, explained through theory, and confirmed by countless observations. It ensures the stability of matter, the universality of atomic structure, and the predictability of chemical reaction. It underlies conservation. It underlies conservation laws, experimental discoveries, and advanced technologies. At the same time, it points to deeper mysteries about the fabric of reality. Charge quantization is not merely a detail of physics, but a cornerstone of our understanding of the natural world. The universe at every scale reminds us that discreteness is as important as continuity. Atoms are discrete, energy levels are discrete, and charge is discrete. The fact that we live in a world where charge comes in fixed, identical amounts is what makes matter stable, life possible, and the cosmos ordered. As research continues, charge quantization will remain a guiding principle shaping our exploration of both the smallest particles and the largest structures of the universe. All right. That is the end of my topics. I hope you guys did enjoy. If you did, just remember to like, subscribe, share, make comments, give some feedback, give, t- tell me what you think. If you have anything to add to it, add it down in the comments section. Love to hear what you have to say. Um, we are at 1 hour and 11 minutes. So I'm glad about that. I know my streams have been a little bit shorter here recently, and I'm just really glad that I was able to actually pull up uh, enough 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 of my topics to make it over an hour, or at least make it to an hour, close to an hour and 15 minutes. So, yeah, we have a Lurker1 on YouTube chat. Yes, thank you for stopping in. And greetings and salutations to you as well. Yes, there are people here. That would be me. Um, molten magnetism fields are difficult. And yes, I agree with you on that. That is something that I believe I kind of went over. I didn't really hit it specifically, but I do have to admit that's exactly where I was going with that when I was explaining the part about the Earth and the magnetic field that the Earth produces that also reflects the energy from the sun away from the Earth in the atmosphere. So, yeah, um, I appreciate you for making your comments and everything, and thank you as well. He says, oh, okay, thank you, but a live stream that is that's strange. I'm wondering if he's thinking there's a absent of a host. No, I'm the host, dude. Um, yeah, he's like, okay, thank you, but a live stream that is absent a host seems weird. That would be me, dude. I'm the host. Yeah. Okay. So thank you for stopping in and making your comments, though. That's greatly appreciated. Uh, Thank you. So, but it looks like I have another person in Kick that is wanting to sell me goods. So there's nothing there. Let me go in here. Oh, wrong one. I am trying to uh, check out Rumble real quick, and after that, I should be done. I'm wanting to see if anybody has made any chats. Nope, nobody. So it looks like we are good to go. If you guys want to check out my streams for Wonderful World of Weirdness, you can find them on Rumble as well as YouTube at The Wonderful World of Weirdness. I'm also streaming on Kick and D Live at Roger underscore Hanson. You can find me there at my actual name. Now on Twitch, you can find me at Infamous 1969. So that's where you can find us. So, and I went and checked Twitch and Kick out. There was nobody in the comment section, so I am good to go. So, like I said, I hope you guys enjoyed. If you did, thank you for I'm really glad that you stopped in to listen to us, and I hope you have a good day. I'm uh, I'm done after reading for an hour. I, uh, I get to where I really don't want to make too many comments unless I have to. You know what I mean? I apologize for my bad reading. I've been working on trying to read better when it comes to these topics, and hopefully someday I will. So I hope you guys have a good day, and I will talk to you later.